to describe nature, it certainly has to contain the standard model. It has to contain the fields of the standard model, the interactions of the standard model, because we know that those exist. So the problem is, how do we extend the standard model to make it a supersymmetric theory? So first of all, let me make a reminder on the standard model, what it is, etc. I remind you, remember, these are the ingredients that you have to specify to define a gauge theory. So the standard model is defined by this gauge group. This is SU3 of color, QCD, and this is the electroweak group, which is spontaneously broken to electromagnetism by the type of the Higgs. Then you have to specify the matter fields and their quantum numbers under the standard model group. And the matter fields here is also to introduce the notation. No? You know that in the standard model, the left-handed quarks and the left-handed leptons are grouped in doublets of this SU2. So U and D are grouped in what is called the quark doublet. Neutrinos and charged leptons are grouped in what is called the lepton doublet. Here I denotes the number of the family of the standard model. The standard model has 3 families, so I is 1, 2, or 3. And then on top of this quark doublet and lepton doublet, you have the right-handed quarks and leptons, or more precisely, you remember here I'm using this notation in which the field without C denotes the left-handed object, and the field with the C denotes not actually the right-handed object, but the conjugated of the right-handed object, because if you remember, I want only to use left-handed fields. In any case, this is the notation. These are therefore the fermions of the standard model. You have to specify the quantum numbers under the gauge group, and you know what the quantum numbers are. The quarks, the left-handed quarks are triplets of color. They have 3 colors. We introduce the minimal number of fields that necessarily have to be there. Then there's no limit to your fantasy. You can add other fields, whatever you want. But the minimal thing that you have to do is this one. So first of all, the group is the same as the standard model group. Again, you could consider larger groups. For example, if you want to study unification, you could consider SU5 or SO10 as a group. But here we want to, again, to do the minimal thing, so we just consider the standard model group, which we know for sure is there. And then each of these fields, you remember the crucial point, must be part of a supersymmetric multiplet of field. So each of these fields must be part either of the chiral, of a chiral multiplet of fields or of a vector multiplet of fields. Remember, these are the 2 types of supersymmetric multiplets of fields that are present in the theory. And so we have to choose for each of these fields whether they belong to this type of supermultiplet or this type of supermultiplet. For the gauge bosons, the choice is obvious. All the gauge bosons always are part of a vector doublet of fields, because this is the only one that contains a vector field. This doesn't contain a vector field. So the gauge bosons are necessarily part of this type of supersymmetric multiplet. And so this means that the gauge bosons are accompanied, as we already saw the other time, are accompanied by a fermionic partner, which is called the gaugino. So we have the gauge boson and the gaugino. And the gaugino is a fermion. So in particular, we have these gauge bosons in the standard model. We have the gluons, and the gluons come together with partners that are called the gluinos. The W's come with partners called Winos, and the B boson comes with a partner called Bino. What about the fermions of the standard model? For the fermions of the standard model, we have 2 options, because both this multiplet and this multiplet, they both contain a fermion, here and here. So, are these fermions part of such a chiral multiplet and therefore accompanied by a scalar, or are they part of a vector multiplet and therefore accompanied by a vector? Well, it's easy to see that they must be part of this type of multiplet. They must be accompanied by a scalar. And why is that? Because if they were part of a vector multiplet, there should exist vectors with the same quantum numbers as the standard model fermions. And you see that there are no gauge bosons that have the same quantum numbers as the standard model fermions. So the standard model fermions must be something else. They must be part of chiral multiplets. In this case, so they are accompanied by scalars, scalar partners, and in this case the partners are called sfermions, so you prepend this S, and the S is for scalar. No? It's a contradiction, scalar fermion, but this is the terminology. So in particular, the leptons of the standard models are accompanied by what are called sleptons, and the quarks are accompanied by new scalar particles that are called squarks. And finally, the Higgs. The Higgs certainly must be part of a chiral multiplet, because there is no scalar in this vector multiplet. The only question is whether the Higgs, which is a scalar particle itself, needs a new chiral multiplet, or if perhaps we can identify the Higgs with the scalar component of one of these fermions. Each of these fermions we've seen as a scalar partner, so maybe the Higgs is one of these scalar particles. If that's the case, the Higgs should have the same quantum numbers as the fermions of which it is a partner. And you see that there is indeed a fermion which has exactly the same quantum number. You see that this lepton doublet here has the same quantum numbers, 1, 2, minus 1/2, as the Higgs, 1, 2, minus 1/2. So the Higgs in principle could be the scalar partner of a lepton. However, this is not possible, because it is true that these two fields have the same gauge quantum numbers, but they have a different lepton number. So, in other words, if you identified the Higgs with the scalar partner of a lepton, you would have a huge amount of lepton number violation. So you would have huge neutrino masses, and the theory wouldn't be viable. That's why you need to introduce a new chiral superfield to account for the Higgs. So the Higgs must be something else. So the Higgs is part of one of these chiral superfields, which means that it is accompanied by a fermion, which is called Higgsino. Now the fermions, the supersymmetry fermions, are called with inos. And finally, the last thing that I have to tell you is that in the standard model you only have one X. In supersymmetry you are forced to add two Higgses called H up and H down. Sometimes they are also called H1 or H2. And the reason why you have to add two Higgses and not just one is that if you added only one X, you would have anomalies in the theory. Because you remember, maybe, I don't know, probably you've seen it in the lectures of Professor Slavnov. In a gauge theory, you could have anomalies that are very dangerous. These are things that destroy the gauge symmetry of the theory. And whether you have anomalies or not depends on what are the fermions of your theory. So in the standard model, the Higgs is a scalar. So you can have one scalar, two scalars, three scalars. Who cares? There's no problem with anomalies. But in supersymmetry, the Higgs is together with a fermion. So you have to be careful and check whether this new fermion doesn't introduce anomalies in the standard model. And indeed, if you added only one Higgs, you would have anomalies. That's why you need to introduce two Higgses. Okay? And there's also another reason. Because in the standard model you can use only one X to generate both the up quark masses and the down quark masses. And the reason is that, you know, here you need two things with different quantum numbers, with opposite quantum numbers. But in the standard model, you can